question?
You can look. Okay. It's number 9 on what's our next one? A13 or like the one we currently know.
Which one are we currently on?
The integral.
The integrals?
5.1.
Okay, can you tell me what it is?
It's x squared plus the square root of x plus 1 over x squared.
And we're supposed to find the integral of that.
Yes.
Okay, we can do that. But the thing is, we have to take anything that looks like a product or a quotient and make it look like a sum first. So as I take the square root sign off and put a 1/2 power, I'm going to break that up into 3 separate fractions. I'm going to write that like x squared over x squared plus x to the 1/2 over x squared plus 1 over x squared.
So would that work out the same if I like multiplied it all by
X to the -2? It should. If you did it correctly, this reduces to 1. Here we subtract exponents. So 1/2 minus 2 is 1/2 minus 4/2. So this becomes an x to the -3/2. And then this is an x to the -2. So multiplying by x to the -2 should get you to that step. And now that I have terms separated by plus signs written as x to a power, we integrate by adding 1 to the power and dividing by the new power. So the first thing I encounter is a 1. The integral of 1 is just x. If I add 1 to a -3/2, that's -3/2 plus 2/2. So I get a -1/2. And then I'm going to divide by that -1/2. And then if I add 1 to the -2, I get x to the -1, and I divide by that -1. And then we tack on the constant of integration. And I guess the last step should be to write everything with positive exponents. So that answer's fine. But with positive exponents, it looks better. If you divide by -1/2, you flip it up and you get a -2 up here. And then the x to the 1/2 is on the bottom. And then this minus sign is going to come up here, and then I have a 1 over x. Okay. Break up products, break up quotients, and then integrate term by term.
I always forget the 1. Every time I simplify.
Every
I forget
time.
the 1.
You find yours? That was it. Now you can't do this if I had 2 terms in the bottom added together. Can't do it then. Okay, you can only break it up into 2 separate fractions if there's a single term down there. If there's a constant, there's no problem, right? If we're going to integrate 4x plus 2 all over 5x to the 5th. You can just leave the 5 down there. You can write this as 4x over 5x to the 5th plus 2 over 5x to the 5th. So if you're multiplying through by the negative power, leave the 5 down there. You just multiply by x to the -5th. And so I can break this one up as 4/5 x to the -4 plus 2/5 x to the -5. And then we add 1 to the power, divide by the new power. So keep the 4/5 there, add 1 to -4 and get a -3. Keep the 2/5 there, add 1 to -5 and get a -4. So I can put these together and write that as a -4/15. And then move the x down here. Put these together, I can cancel 2 into there and get a -1/10. And then put the x to the fourth down there.
So what do we do if there's two separate terms on bottom?
Hopefully we learn some new techniques to help us take care of that. Right now, if there's two separate terms, we look for, is that those two separate terms making an arctangent function? So we'd have to have a constant in the numerator. But if there's two separate terms, we gotta wait until we get to the end of chapter 5 to figure that out. And we'll be there sooner than you know, like maybe today.
Okay.
Anybody else?
Take it away.
Take it away. It's my turn. Dang. Okay. So as an overview, we have our basic antiderivatives in section 5.1. In section 5.2, we had an introduction to what a Riemann sum was by looking at left sums and right sums to approximate area under the curve. And some general version of this would be called a Riemann sum. And so in section 5.3, there's more of that, more about the Riemann sums. And in section 5.4, we learn something called a definite integral. The definite integral as area. And then we look at some properties of the definite integral. So I kind of want to put all that together today and step our way through everything, except for the 5.1. I think we've beaten that one up pretty good. So let's do an approximation problem. Okay, so for example, let's let f of x be, say, 6x squared plus something. So let's move it up to 2. And let's use a left sum and then a right sum. Approximate the area under this curve from, say, x is -1 to x is equal to, let's go 3. And in part A, let's use n is equal to 4 equally spaced rectangles. And then let's double it in part B. Let's use n is equal to 8. And then we'll look at how this is related to our integrals. And I might even compute an actual Riemann sum for you using the limit. If you're good, if you behave yourself, So what's the graph of this thing look like? Y is equal to 6x squared plus 2?
Parabola shifted up and
And that's it, parabola shifted up, right? So let's make a big old picture over here. That room right there. You're all here, so I don't know why I'm recording this thing. You guys don't go back and look at them later, do you? Oh, I should shut it off? Or do you go back and look at it later?
we keep it on for this one.
Keep it on for this one? You think I'm gonna blow you out of the water on this one? Or you feeling the sleepiness come on? No big deal, I can do it. Okay, so it looks like a parabola opening upward. When x is -1, I get the ordered pair -1, 8. So let's put that in about right here. When x is 0, I get y is 2, so if that's 8 here, and that's 4, and that's 2. And then when x is 3, oh gosh, when x is 3, I'm way the heck off the page. So I'll just fake it. 9 times 6 is 54, plus 2 is 56. So that's as high as I can get. That's the ordered pair 3, 56. And so our parabola looks something like this. Way out of scale, but who cares? And we're looking for the area underneath that graph from x is -1, x is equal to 3 above the x-axis. So this funny looking shape under here. So the interval on the x-axis has a length of 4. I'm going to break it up into 4 equally spaced rectangles, so I'll have that as the base width. So that's at 1, and that's at 2, and of course that's at 0. So here's the 4 rectangles, when I put the top on them. When I'm making a left sum, I go to each rectangle and I make the height of the rectangle correspond to the y value at the left end point. So here I am in rectangle number 1, and my left end point is here. So it's this rectangle. In rectangle number 2, my left end point is here, and so I make that rectangle. Rectangle number 3 has this as the left end point, so we have that rectangle. And then rectangle number 4 has this as its left end point. So I use the area of those 4 rectangles to approximate the area under the curve. So here's what we got to do. We got to make a sum. We're going to make the sum, evaluate our function at the left value, the leftmost x of each subinterval, and then multiply by the width of each subinterval. In this particular example, the width is going to be 1, so delta x is just 1. And my left x's are going to be -1, 0, 1, and 2. And this means add them up. Let me rub this off. So I'm going to write down next that I'm going to find f of -1, add to it f of 0, then f of 1, and then f of 2. And then multiply all of that by that equivalent width. That's base is the delta x, height is the f of x. We get those numbers in the brackets by plugging them into here. I already have f of -1, that's 8. F of 0 I already have, that's 2. F of 1 is also going to be 8. Now it's your turn. Tell me what F of 2 is. 26. 2 squared is 4, times 6 is 24, plus 2 more is 26. And then we said delta x was 1. And so I have 10 plus 26 is 36, plus 8 is 44. So that's roughly 44 square units of area.
How do you find the delta x?
Delta x is how wide I make these. So in general, delta x on the interval from A to B is going to be the length of the interval divided by the number of rectangles you want to make. So our B was 3, and our A was -1, so 3 minus a -1 with 4 rectangles. That makes each of them 1 unit wide. Yes?
Why do we have to multiply each f value by, I mean, like I get on this example, why? But like, why doesn't it have to be, like, let's say it was 2. Why doesn't it have to be 8 times 2 plus 2 times 2? Like,
It is. I mean, it's
does that
base.
give the same answer?
No, it's the base times height. Base times height.
Right, but like how we multiply the whole sum by.
Right, it's just the distributive property. I factored it out so I wouldn't have to do it one step at a time. That was my laziness.
Got it. I don't know why I thought that'd be different.
Okay, so now let's make a right sum. I think I can fit it right here. So I got to add up the value of f at each of the right x's for each rectangle times the delta x. And now my rightmost x's, so here in rectangle 1, the rightmost x is 0. In rectangle 2, the rightmost x is 1. In rectangle 3, the x on the right is 2. And then x is 3. So I want f of 0 plus f of 1 plus f of 2 plus f of 3 added together times delta x. Oops. Get that in there, move my camera over a bit. I'm going to zoom out. You silly thing, turn a bit. Maybe it fits. There we go. So f of 0 was 2. So we're going to have 2 plus 8 plus 26 plus 56. I'll multiply by our delta x, which in this example is 1. So let's see, 56 plus 26 is 82. 82 plus 10 is 92, times 1 is 92. So our idea is that the actual area is some number between 92 and 44. That's a pretty big gap. So I'm thinking I could do better if I put 8 rectangles in here. So I'll erase that picture and put it over here, or not erase the picture, just redraw the picture and put it over here. Keep going from -1 to 4 with 8 rectangles. The delta x is going to be, 3. 3 minus a -1 divided by 8 rectangles. So each rectangle has a width of a half. So my 4 rectangles, oops, let's move that over a little bit. My 4 rectangles have here, here, and here, 0, 1, 2, 3. Now cut those in half. So here's a -1/2, a +1/2. Oops, I didn't put it through the right point. Fudge, fudge, draw it again. I have to move that parabola up. All right, there we go. So, oh gosh, I made it too big again. It's hard. There's -1, there's 0, there's 1, there's 2, there's 3. And then I'm going to cut those in half. So there's -1/2, +1/2. This would now be at 3 halves, and this one's at 5 halves. So my 8 rectangles, 1, 2, 3, 4, 5, 6, 7, 8. Move over. Okay, so when I use left endpoints, my first rectangle, I'm making pink this time. That yellow's hard to see. My first rectangle is going to have this height. So I use f of -1. My second rectangle, I use f of -1/2 to give me the height. My third rectangle, my left endpoint is f at 0. Then f at 1/2. Then f at 1. Then f at 3 halves. Then f at 2. And then f at 5 halves. So I'm going to write those out as my left sum. And each time delta x is going to be 1/2. So I'm going to factor that 1/2 all the way out. And so the numbers I need are, again, f of -1, f of -1/2, f of 0, f of 1, f of 3 halves, f of 2, and then finally f of 5 halves. All of that multiplied by the width, which in our example is going to be 1/2. Sound good? Okay, we get messier numbers because remember again, f of x is equal to 6x squared plus 2. I already have some of these numbers. Lucky me, I erased them. F of 0 was 2. Oops, I should have had a 1/2 in here. 1, 2, 3, 4, 5, 6, 7. Yep, I need one more. Squeeze an f of a half right in here. I do have f of 1. F of 1 was 8. F of 2 was 26. And f of -1 was also 8. So now we're going to get all those halves. F at -1/2 is going to be 6 times 1/4 plus 2. So that's 3 halves plus 4 halves will give me 7 halves. And f of 1 half is going to be the same. Now f of 3 halves is going to be 6 times 9/4 plus 2. Let's see. Let's make that a half. Let's make that a 3. So that's 27 halves plus 4 halves. 31 halves. That was this one. And then finally, f of 5 halves gives me 6 times 25 over 4 plus 2. So that's 75 halves plus 4 halves gives me 79 over 2. Delta x was a half. Yeah, thanks for the help. All right, let's add them up. Let me do the halves first. 79 plus 31, that makes 80, 90, 100, 110. So that's 110 over 2 plus 14 over 2 is 124 over 2, which gives me 62, I think. So 62 plus that 8 makes 70, plus 10 makes 80, plus 26, 80, 90, 106, over 2 gives me 53. As the area approximated that way. You look like you believe that number? Okay, now let's make a right sum. So the only difference in the right sum is that we're going to take this thing and evaluate f at the rightmost x times delta x. So we scoot over one x value, and we'll have f of negative 1/2 plus f at 0 plus f at 1/2 plus f at 1 plus f at 3/2 plus f at 2 plus f at 5/2 plus f at 3, and then all of that multiplied by delta x. Let me count my rectangles. 1, 2, 3, 4, 5, 6, 7, 8. There's my 8 rectangles. Got all these numbers but the last one, so let's put them all in here. F of negative 1/2 was 7/2. F of 0 was 2, and another 7/2, then 8, and 31/2, and 26, and 79/2, and then f of 3 was that 56. So let's see, if I go back here and take the 8 out of here, 8 from 106 is, what's 8 from 106? 98? 98 plus 56 is 154. 2 times 7 is 14, so that time it gives me 77. So now I think that my actual area is some number between 77 and 53. And I keep doing this an infinite number of times. But I'm not going to do it an infinite number of times. I'm going to do it symbolically. And then take a limit and let the number of rectangles go to infinity. And then show you how that compares to what we call the definite integral. But do you have any questions on what I did here? Just crunch them out. Back in the day, we used to take those TI-85 calculators and make a program, and all you had to do was punch in the function and the number of rectangles, and it drew it for you, and it calculated a left sum and a right sum. So I'll make you do it for like 4 or 5 rectangles by hand. Okay? Now this next part, I'm not going to make you do. I'm going to do it just because I really enjoy doing it, but I want you to see the theory and where the definite integral comes from. And I'm going to use this as my example. I'm going to compute an actual Riemann sum. In an actual Riemann sum, we take our interval and we divide it into n congruent parts. Then we pick a general format, either a left sum or a right sum. Doesn't matter, because we're going to take n to infinity, which makes these essentially the left endpoint and the right endpoint almost exactly where they are. You can even do a midpoint sum if you wanted to. It really doesn't matter because we're going to crunch those intervals down into almost nothing. So that we're filling this up with a bunch of vertical lines. But we're going to do it with a limit instead of with pink chalk. So let's see. I need the function, I need the -1 and the 3, and then we're going to figure out how to do this in general. Let's keep that guy there. So now we're going to subdivide the interval from -1 to 3 into n rectangles of width delta x, which is in general again b minus a over n. So in our example, it's 4 over n. And I'm going to do a left sum. So I'm going to each time start with my left endpoint. Then I'm going to take left endpoint plus 4 over n, then left endpoint plus 4 over n plus another 4 over n, then left endpoint plus 3 4 over n's, and so on. So here's the interval. So my first subdivision occurs at -1 plus 4 over n. Then I add another 4 over n, so I'm at -1 plus 2 times 4 over n. Then I add another 4 over n, so I'm at -1 plus 3 times 4 over n. Until I get down, say, to the kth subinterval. So maybe I should do a right endpoint. I will do right endpoints. So my first rectangle, that's my first right endpoint. Second rectangle has a 2 here. Third rectangle has a 3 there. So the kth rectangle will look like -1 plus k times 4 over n as being the right endpoint. Yes, question, stretching? So if I'm doing a right sum, then I find f of the right endpoint times delta x. And I put it in my summation. I want f evaluated at the right endpoint times our delta x. And I'm going to do this from k is equal to 1 to n, and then I'm going to let the number of rectangles go to infinity. So f was 6x squared plus 2. My right x has this as its general form. I'm going to plug that in for x. So it's going to have this summation here, 6 times -1 plus k times 4 over n, I'll get rid of the parentheses, squared plus 2 times delta x, which was 4 over n. You with me to there? Now I'm going to square that. I'm going to square this thing by taking -1. Let me write that as 4k over n. We're going to square that right here. So I get -1 times -1 is 1. Here I'm going to get -4k over n, and there's another -4k over n for a grand total of, let's make it -8. -8k over n. And then I square it, and I get 16k squared over n squared. Now I'm going to send the 6 through there, and as I do that, I'm also going to add the 2.
Wait, would it be 64 or 6 when we square it?
4 times 4 is 16.
On the square. Okay. No, I got it.
Okay?
You're
4 times 4 is 16, k squared over n squared. Now, when I send a 6 through here, this is a 6, but then I got +2, so let's go ahead and write 8. And then 6 times 8 gives me 48k over n. And then 6 times 16 gives me 96k squared over n squared. And so my next step now is to multiply 3 by 4 over n. This is algebra, right? So 4 times 8 is 32 over n. 4 times 48, 4 times 8 is 32, carry the 3, 16 plus 3 gives me 192k over now n squared. And then 4 times 96, 4 times 6 is 24, carry the 2. 4 times 9 is 36, plus the 2 gives me 38, k squared over n cubed. This sum is on k. I'm going to n, and then I'm going to take a limit. All right, so that's a finite sum, which means I can break it up into 3 different pieces. And that's what I'm going to do next. Get over there. It's all out. It's an algebra problem right here. So I'm going to write that as the sum from k is equal to 1 to n of 32 divided by n minus the sum of 192k over n squared plus 384 k squared over n cubed. All of these summations are over k. So if it doesn't involve a k, I'm going to factor it out and put it right in front of the summation symbol. So none of these involve a k. I'm going to factor it out and leave a 1 behind. When I pull this out, I have a k left behind. So negative 192 over n squared times the sum from k is equal to 1 to n of just the integer k. And then here I leave a k squared behind. Now I want you to think about what this looks like. That summation means I'm adding 1 to itself a total of n times. That means 1 plus 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 1 until I've done that n times. So that should add up to n, right? So that's what that adds up to. This one's trickier. This one means I'm adding 1 plus 2 plus 3 plus 4 plus 5. Each time k gets bigger, and I keep doing that until I get down to n. So I'm going to convince you of a formula for that. So first formula. Sum from k is equal to 1 to n of 1 is just n. The sum from k is equal to 1 to n of k means 1 plus 2 plus 3 plus 4 on out to n. I want you to do this for me. Just add up the numbers 1 through 10. Add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Hurry, get her done. Move that way. The thing that slows you down in adding up the first 10 numbers is you're trying to add them from left to right. But don't do that. Add them first number plus last number. 1 plus 10 is 11. Now I'm going to add the second number and the second to last number. 9 plus 2. That's 11 again. The third number and the third to last number. 3 plus 8. 11. The next two. 4 plus 7. 11. The middle two. 5 plus 6. 11. So when you're adding up the numbers 1 through 10 that way, I get a sum of 11, a total of how many times? 5. So 5 sums of 11 means the numbers 1 through 10 add to 55. That's the way I'm going to add these here. I add the first number with the last number. That's going to be the sum that I get over and over and over again. And the number of times I get it is the total number of pairs that are in that list. So here, my first number plus my last number is n plus 1 times the number of pairs that are in that list. Well, I've got n things I'm adding together. If I pair them up, that means there are n over 2 pairs. Check it out. When n is 10, we said that added to 55. So 10 plus 1 is 11, times 10 is 110, divided by 2 is 55. So that's what I'm going to put here. The sum of the first n integers is n plus 1 times n, all divided by 2. Now I'm going to convince you of this formula. This one's not so obvious. The sum of the first squares means I'm adding 1 squared time plus 2 squared plus 3 squared on out to n squared. So I'm adding 1 plus 4 plus 9, blah, 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 out to n squared. And here's what I claim the formula to be. I don't claim it to be, I'm looking it up. N times n plus 1 times 2n plus 1 all over 6. Let's see if you believe that. Let's add the first 3 up. So for n is equal to 3, we have 9 plus 1 is 10 plus 4 is 14. Let's see what happens if we put n as 3 over here. 3 times 4, 6 plus 1 is 7 times 7 divided by 6. Well, let's see. 3 goes into 6 twice. 2 goes into 4 twice. 2 times 7 is 14. So I didn't make that up. That's a known formula from way back whenever. But that's what I'm going to put right here. I put the n times n plus 1 times 2n plus 1 all over 6. So here this n will cancel. Here one of these n's cancel. And let's just leave it like that. And now remember, our last step is take the limit as n goes to infinity. So this is just a 32 minus, I guess I can reduce that. 2 times 9 is 18. 2 times 6 is 12. And then I have n plus 1 divided by n. Let's see if 6 goes into here. 6 times 6 is 36. Leave me 24. 6 times 4 is 24. All right, I'm going to cancel one of these n's, and that leaves me an n squared. And so I have n plus 1, 2n plus 1 over n squared. Here's the only step that involves calculus. We're going to take those limits. So remember how we take limits to infinity? Well, this one's easy. There's no n, so that stays at 32. So now we're looking in those parentheses. N is going to infinity. The power on top is the same as the power on the bottom. What's the limit of the stuff in the parentheses? Well, take L'Hopital's rule one time. What's the derivative of the top divided by the derivative of the bottom? 1. Limit inside here's 1. Just the ratio of the coefficients. Right? So the limit in here is 1. That gives me a negative 96. Here again, don't look at the 64. If I were to multiply this out, I'd have a 2n squared as the highest power of n, and a 1n squared as the highest power of n. So what would we say the limit was going to be when n goes to infinity?
The coefficient.
The coefficient. So it's going to be 2 over 1. So we do those limits, and here's what we get. We get 32 minus 96 plus 64 times 2. So 64 times 2 is 128. 128 plus 32 is 160. Minus 96 is 64. So I think the exact area is 64 square units. Exact, because we put an infinite number of rectangles in there. So what I did is I calculated something called a Riemann sum. I evaluate the function at some stated x. We usually call that stated x star, because it doesn't have to be a right endpoint. Could be the midpoint, could be the left endpoint, could be just any old special x in there. But you write the recursion in terms of your delta x, distribute everything out. If you're working with polynomials, we have known formulas for those summations on k to give you functions of n. So now everything's written as a function of n, and you can take the limit, and there you get it. Well, we're limited by the number of formulas we have, so that's why we're not going to do that in practice. Just like we don't always use the definition of the derivative to calculate the derivative. We only did it for the easy examples. So now I want to show you that this thing called the Riemann sum becomes a definite integral. So we're going to say that in general, the Riemann sum of f at some special x star, we're summing it up over k, times delta x, and we're going to let k go from 1 to n, and then take the limit as n goes to infinity. This is called a Riemann sum. The limit of the finite sum becomes an integral. This just becomes the general formula for f. This becomes the general differential in x. And then summing from 1 to n says I'm covering the entire interval from a to b. And this part here is called a definite integral of f on AB, with the assumption that f is continuous. We can't do this for a function that has lots of goofy spots in it. Then remember how we do this. If I don't have the numbers on there, you find an antiderivative. And then we're going to evaluate that antiderivative at the two endpoints. We put the right endpoint in first, then we put the left endpoint in, and then we subtract. And so what I've written here is called the first fundamental theorem of calculus. First fundamental theorem of calculus gives us the connection between a derivative and an antiderivative. The derivative of this is that, the antiderivative of this is that, and it can be interpreted as area under the curve when our function is positive. So what I want you to compute now is put our function in there, put our 6x squared put our 6x squared, where'd it go? Right there. So let me move it over. We're going to go right where I wrote. Remember the 64. Save that. And I want you to compute the definite integral from, what did I say, -1 to 3 of 6x squared plus 2 dx. Compute that definite integral. You're going to add 1 to the power, divide by the new power. And so what do you do when you integrate 6x squared? 2x to the third, if I agree. Add 1 to the power and you get a 3, divide by 3. It's going to give us 2x cubed. What about the 2? Integrate it, 2x. That's the antiderivative. That's what I mean by that capital F. Now you're going to put the 3 in for each x. And then you're going to put the 1 in for each x. And then you're going to subtract. So 3 cubed is 27. 2 times 27 is 54. 2 times 3 is 6. Keep working down the line. 1 to any power is 1, so 2 plus 2 gives me 4 out here. So 54 plus 6 is, oops, this should be a -1, sorry. Sorry, -1. And so that's going to put me a -4 in here because -1 cubed is negative, and -1 times 2 is -2 in each place. Kind of had me scared there for a minute. 54 plus 6 is 60, minus a -4. Guess what that gives us? So that's why we're not going to compute Riemann sums. We can compute definite integrals and get the area much faster. Even though that was kind of fun. I enjoy doing that. Here's algebra and magic formulas. Okay? All right, so this thing, the definite integral, if f is a positive continuous function above the x-axis, then that represents area. And so it has some properties that are related to area. Let me give you the properties of the definite integral. We're going until 2. So take a quick break. Take a break, and then we'll pick it up from the properties of the definite integral. Don't trip over my cord. Jump, jump.
I have a question.
Yes.
Okay, so when you're doing definite integral, you do not have to put your plus.
You don't, because there would be a plus c here, and a plus c there, and you'll subtract.
Oh,
So that part doesn't matter.
okay, that makes sense. Thank you.
You lose it at the end anyway. I suppose I could put one on my work. Why was that funny?
Really?
What?
Genius.
No, I do it every semester for my honor students.
I love it. I was watching it.
I like to watch people paint, but I don't like to paint.
Yeah. There's a meteor shower
Tonight?
here in Lubbock.
Can you
I don't know if
see it
it's
here in Lubbock?
I'm trying to.
Is it really a meteor shower, or is it just the
I don't know.
whatever that space lab is up there dumping their space garbage?
Well, there's supposed to be a pink moon on the 26th, so we'll see if that's
Really?
it or not.
And now I'm gonna have that little song stuck in my head. Pink, 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 pink moon.
15 to 20 meters per hour.
Wow, what time does it start? Like darkness?
Let me see. I'm trying to figure that out.
So we all get our sleeping bags and lay out in the backyard? What if it's as cold as it was last night?
During the second half of the night.
So for me, that's from 8 to 10. Second half of the night. Nope, not seeing it. I'll watch it on CNN tomorrow.
Excuse me, Miss Schovanec.
See what I'm gonna do next. I like the feel of that chalk. All right, there's the graph of f of x is equal to 2x minus x squared on the interval from 0 to 2. On the interval from 0 to 2. What I want you to do is approximate the area using n is equal to 4 rectangles. And left endpoints. Get a left sum out of that. It turns out since this is symmetric around the one, the left sum is the same as the right sum. So break that up into 4 rectangles and let me see if you can crunch out a left sum to approximate the area. You get 5/4 as your approximate area. Are you getting anywhere near there? Cut the interval from 0 to 2.5, and then hit each of those in a half. This is at a half, and this should be at 3 halves, and then left endpoints. So your first rectangle doesn't even have any height at all. Your second rectangle has that as its height. Your third rectangle has that as its height, and your fourth rectangle has that as its height. First one has a height of 0, and whatever that is. and that one, and that one. And if you think about what the the right sum would look like, it'd be the same but shifted over, so you should get the same number. Right? Okay, so with the left endpoints, we need to find f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. Those are all the heights times the width. And so I just surmised that the width was 1/2, but again, b minus a over n. Confirm that. My b is 2, my a is 0, and n was 4. Each delta x has a width 1/2. F of 0, we're putting 0 in here, and we're getting 0. Now when you put 1/2 in here, you get 2 times 1/2 minus 1/4. So you get 1 minus 1/4, that'll be 3/4. F of 1 is going to be 2 minus 1 is just 1. F of 3/2 is 2 times 3/2 minus 9/4. So that's 3 minus 9/4. 3 is 12/4 minus 9/4. That's going to be 3/4 again. See where I got those numbers? And then multiply that by delta x, which he said was 1/2. So 3/4 plus 3/4 is 6/4, plus 4/4 is 10/4. 10/4 is 5/2 times 1/2 gives us 5/4 as our approximate area. And like I said, there's no reason to do the right sum, because if you did the right sum, you'd get these pink rectangles, and by symmetry of this particular graph, it's the same as the left sum. Now I want you to compute the exact area. Which we said was given by the definite integral from 0 to 2 of the function that we graphed. So you're going to find the antiderivative of 2x, the antiderivative of x squared, plug in the 2, plug in the 0, and out comes the exact area. We'll skip the entertaining part that I did with the Riemann sum. Too much excitement in one day. Did you get it yet? 4/3? Good. Because when you integrate 2x, you get x squared. When you integrate x squared, you get x to the 3 over 3. This tells me now to put numbers in. It's always top minus the bottom. So I get 2 squared minus 2 cubed over 3. And then 0, 0. So those ones will give me 0. So 4 minus 8/3. 4 is 12/3. minus 8/3, the exact area is 4/3. Okay? Pretty neat, huh? A derivative of a function gives you what's going on at a single point, right? Tells you the slope at a point. But an antiderivative of a function adds things up over an interval. So it does quite the opposite. It takes a bunch of little lines, adds them together to get you the area under the curve. Where a derivative takes something over an interval, shrinks it, and gives you slope at a point. Okay, so with area in mind, integrals can be used for more than area, just like derivatives can be used for more than slope at a point. But just thinking in terms of area, let me write down some properties. So we're going to consider a continuous function at an interval from A to B. So properties of the definite integral. Well, F and G. Because the things that you do with an indefinite integral, you can do with a definite integral. Like if I've got two continuous functions added together over an interval, I can do them piece by piece. You can integrate term by term through a polynomial. We did it here without even calling that a property. Do things term by term. I didn't worry about numbers because you can always put numbers on at the end. So just like with an indefinite integral, I can factor numbers out that are multiplied. So those are the same as the properties of what we call the indefinite integral, just the general antiderivative. You can do that with the definite integral. Now, this one might be obvious. What if the upper limit is the same as the lower limit? What if I'm just integrating and finding area above a single point? Or what if I took my antiderivative and plugged the same number in both times and then subtracted? What should we get? 0. The integral above the area underneath a single point is 0. Because that one little line doesn't have any dimension to it. My delta x is 0. All right. Now think about addition. This, whoa, come on. Says that you compute this integral and put in the top number, then the bottom number, and subtract. What if I wrote that backwards? What kind of number would you get if I put the 0 in first and then subtracted the 2? You'd get the same thing, but negative. If you change the order of integration, you just change the sign of the number on the end. Okay? If you find the area from here to here, it's the same as if you go from there to there, but opposite in sign. Then the last one says this. If I've got a continuous function on the interval from A to B, and I'm going to compute that as a definite integral, I can, if I want, stop anywhere in between, take that area, add it to that area, and I get the same area. The integral from A to C added to the integral from C to B is equal to the integral from A to B. theorem comes in handy if by chance f isn't continuous over the whole interval. Maybe it makes it jump. Maybe it changes shape. Then you can change it under one shape and then under the other, add the areas together. Okay. Here's something that uses those. Suppose you have some mystery function, and when I integrate that mystery function from 1 to 4, I get 8. And when I integrate that same function from 3 to 4, I get 2. And what do you think happens from 1 to 3? I'm going to draw a picture while you write that down, or draw a picture to help you process this. Here's the picture. What this says right here, let's see, there's 1, 2, 3, 4. So we've got some sort of function here. From 1 to 4, that area there is 8. From 3 to 4, that area is 2. That's what these two things say. So now it's asking you, what's the area stuck there from 1 to 3? 6. That's exactly 6. Okay, so that's the additive property here. Ooh, stop that. And what's the area from 4 to 3? It's -2. Same as that one, but I swapped that order, so I changed that sign. Okay? And what about the area from 2 to 2? 0. Right? That's exactly 0 area that I've drawn right there. All right, so part D, how about the integral from 1 to 4 of 6 times f of x minus 5? We're going to kind of use these two here. Break it up into 2 integrals, 6 times f of x plus the integral of 5. Then it says pull the 6 out, tell me what the integral of f of x is, then put the 6 back in. Then hopefully you can integrate 5 all by your lonesome. That was, think of that as 6 times the integral from 1 to 4 of f of x dx. So do the first part, minus the integral from 1 to 4 of 5 dx. Okay? And term by term, and you pull constants out. We said the integral of f of x dx was 8. I forgot the dx, it's there. So this is 6 times 8. This one geometrically describes a horizontal line, y is equal to 5. You want the area under that line from x is 1 to x is 4. So you find the area of a little rectangle. Right? So do it by brute force. What's the integral of 5? 5x. And then you put the numbers in. 6 times 8 is 48. This is 5 times 4 minus 5 times 1. 20 minus 5 is 15. And 48 plus 15 is 63. Yes.
Why did I switch from a minus to a plus?
Where did we switch from a minus to a plus?
So whenever you.
Oh, that was my bad. That's supposed to be a minus. That's a minus, so I gotta subtract again. Could you not have done that before I had to add? I wasted 2 brain cells doing that arithmetic that I'll never get back. All right, what's 48 minus 15? 33. All right, so that's how you use the properties of the definite integral. And now let's just compute some definite integrals. Let me put 4 of them up here, and you guys knock them out. You can make it. You can do it. You can do it. You can do it. First one, integrate from 1 to 4, square root of x dx. Second one, integrate from, oh gosh. Let's go from 1 to 2. 4x minus 1 over x squared dx. Third one. Let's integrate from 0 to the natural log of 3 of 6 times e to the x dx. And then the fourth one, I'll put right here. Integrate from 0 to pi over 4. Cosine of x minus the sine of x. When you mark it, let go. Find the antiderivative, and then use the fundamental theorem of calculus. Take the antiderivative, evaluate it at upper limit minus the lower limit. The answer's down here. Can you help get them? Let me know. Oh, that one I didn't do. This one. Another one real quick. Yeah, there's answers to all of them. Let me know if I can help you. Unless I got one wrong, because Tim is just staring at it. I did it wrong. Yeah. Zero. Two-thirds. Well, no. Okay. Any success out there? You guys want to come put them up here? Who's finished? Give me 4 people. Come put up the in between steps. Walking up there, grab a problem and a piece of chalk. Don't make that squeaky noise with your chalk. You're scared to not make the squeaky noise, or too scared to squeak? Just kind of go easy. Don't be overly aggressive. There's gonna be 3 more volunteers or class member and get on up there, baby doll. All right, give me some. We'll take it. I know, the whole box of 2 pieces in it. You said you want to be a teacher.
I know.
Now's the time to learn.
Chalkboard.
Oh, they're gonna have marker boards or YouTubers. Oh, no, you might teach at a small town school, so you have chalkboards. Appreciate it. Good, good. Okay, so you write it as x to the 1/2. You add 1 to 1/2, you get 3/2. When you divide by 3/2, you put the multiply. So you have 2/3 in front of both of them, 4 to the 3/2 and a 1 to the 3/2. 1 to any power is 1. So this just gives you the 2/3. A 3/2 powers means take the square root first. So the square root of 4 is 2. Cube it is 8. 2 times 8 is 16. So 16/3 minus 2/3 gives you the 14/3. All right, the integral 4x is 2x squared. Think of this as x to the -2. So when you add 1 to the power, you get a -1. Divide by the -1 makes that a plus, and then move the x down to the bottom. So technically, this is a bar over here, telling you you're going to go from 1 to 2. Not an integral sign anymore, but it does mean put the 2 in first, and then the 1. And then crunch, 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 and you get 11/2. Integral of e to the x is e to the x. And so you put the two numbers in, but remember e's and logs cancel each other out. So all you get out of here is the 3. 3 times 6 is 18, minus 6 is 12. Integral of cosine is a positive sign. Integral of a sine is a minus cosine, which gives you a plus here. And then we evaluate at pi over 4. Sine and cosine at pi over 4 are the same. Sine at 0 is 0, cosine at 0 is 1. So you got square root of 2 over 2 added together with itself, so give you 2 of them, and then the 1 from here. Okay? All right, now I'm going to give you 2 integrals, and I want you to interpret them as area, and then to get their value. So interpret this as area under a curve. My problem is. You can't just go inside the absolute value and integrate. You can't just say that's the absolute value of x squared minus 2x. It ain't. I want you to think of what the graph of f of x is equal to the absolute value of x minus 2. Tell me what that looks like. Tell me what area you're finding when you're doing the integral from 1 to 7. And then see if you can use geometry to find that integral. Then the same with this next one. We're going to integrate from 0 to 4 of the square root of 16 minus x squared. By telling me what does the graph of this look like, and what part of the area are you finding? Because you can't just go inside the square root sign and integrate each term and then put the square root sign back on. The absolute value bars are saying keep out, and the square root sign is saying keep out. So think geometry. What kind of pictures are we describing here? What kind of areas are we finding? So what does this look like if I didn't have the bars on it? Y is equal to x minus 2. That's a line with positive slope, right? But part of that line's under the x-axis. From where to where is it under the x-axis? Because the absolute value takes stuff that's negative and flips it up and makes it positive. Where's across the x-axis? That x is equal to 2? Right? So the part that's underneath the x-axis goes up here. Take the absolute value of it, and it looks like that. So you've got a V-shaped graph from x is equal to 1 over to x is equal to 7. We're just finding the area of two triangles. 1/2 base times height plus 1/2 base times height. So you just have to plug those numbers in to find what the heights are, and then add the areas of the two triangles together. Figure out what the heights of those two right triangles are, and then 1/2 base times height for each of them, add them together to get the total area. So when x is 1, 1 minus a -2 is -1, so this is 1, 1. Next is 7, 7 minus 2 is 5. So that's the ordered pair 7, 5. So this triangle has height 1, base 1. So it's 1/2 product of the height and the base. The next triangle has a height of 5. How wide is the base here? 5. So it's 1/2 of 5 times 5. So you have 1/2 plus 25 halves is 26 halves, which is 13 units of area. Those are just a couple of straight lines that made a little V-shaped graph. This one's not a V-shaped graph. To give you some idea what this graph looks like, let's start from here and square both sides. That's what it looks like without the square root sign. And if I put my variables together, do you now recognize what it is that I'm describing here? That's a circle. That's the entire circle of radius 4, centered at the origin. When I go backwards and take the positive square root, then that's just the top half of that circle. Now when I integrate from x is 0 to x is 4, that's only giving me the top quarter of the circle. So it should be 1/4 of the area of that entire circle. Right? That's a circle whose radius is 4. And I'm only looking at x is 0 to x is 4 and where the y's were positive. It's the area of a circle? R squared. So it's 1/4 of pi r squared. What was r again? 4. So 16 times pi divided by 4, that integral has a value of 4 pi. Okay, but that's not what you would get if you ignored the square root sign, put an x here, and made that x cubed over 3, and integrate from 0 to 4. It can't just go inside the square root sign. You won't get anywhere close to that. Okay? For one thing, you'd never get a pi. Okay, so when I said that a definite integral involves taking the antiderivative of the function and evaluating it from a to b, I said that was called the fundamental theorem of calculus. Here we are, 5/4 of the way through the semester. Oh, that's more than one whole way. 5/6 of the way through the semester. Then we get to something called the fundamental theorem of calculus. That's the first fundamental theorem of calculus. Because if there's a first fundamental theorem of calculus, by gosh, there's a second fundamental theorem of calculus. And it says what we've been saying all along. The opposite action to doing a derivative is doing an antiderivative. The opposite action of doing an antiderivative is taking a derivative. Those two operations undo each other. So here's the second fundamental theorem of calculus. You're on the edge of your seat, drum roll. Well, a definite interval produces a number, unless one of your limits of integration is a variable. So suppose I want to integrate, say, from a to a variable amount. And then up here, I'll put some function of t, dt. So what would happen is, if I know how to compute the antiderivative of this, I get a capital F of t, and I evaluate it at x, and I evaluate it at a. Right? So this would be capital F at x minus capital F at a. That's the first fundamental theorem of calculus. Now here comes the second fundamental theorem of calculus. Now suppose I want to take the derivative of that with respect to x. So I'm going to go over here and take the derivative of this with respect to x. What's the derivative of capital F called? Right? And this is a constant. What's the derivative constant? 0. So it says if you differentiate an integral of a function, all you get is the function back, but as a function of the upper limit. No plus c, because it's a derivative. The derivative of an integral that produces a function of x is the integrand as a function of x. That's it. That's the second fundamental theorem. So it tells us how to do this. Suppose I knew how to calculate this integral and I called it g of x. Say it's the integral from pi to x of sine squared of t times the cosine squared of t dt. We don't know how to integrate sine squared. We don't know how to integrate cosine squared. So we certainly don't know how to integrate sine squared times cosine squared. So I couldn't actually define capital F for that version of my integrand. But I can still take the derivative of this without doing that in between steps. Because I know this gives me some function that has this as its derivative in terms of x. And that's what I get. I get the integrand as a function of x. No plus c. This is g prime kills the integral sign and evaluates this at the upper limit. And guess what? There's a chain rule. If I have g of x is equal to, say, for instance, x to the 5th, and I want g prime. Well, I get my integrand as a function of the upper limit. So in here, I would have an x to the 5th. Over here, I have an x to the 5th. But there's more. Times 5x to the 4th times the derivative of the upper limit. So the general version of this says that the derivative with respect to x from a to u of x of f of t dt is equal to f evaluated at that upper limit times the derivative of the upper limit. The derivative kills the integral and gives you back the integrand as a function of the upper limit. There's not a third fundamental theorem of calculus, so you can spend the rest of your little mathematical lives making one of them. So, an important question here. How far do you want the test to go on Monday? I have a review sheet prepared to cover all of chapter 4 through section 5.4. At a minimum, I want to put the left sum, right sums on there. If you want definite integrals on there, I can go all the way through 5.4. You tell me. You don't want the 5.4? That's so easy. Take your antiderivative and plug numbers in.
True. That's true. Well, we're doing it on Monday instead, we've been doing it on Wednesday, so 2 hours on Monday.
Monday, you just have one. Okay, so how about we go through 5.2? 5.2 would be 5.1 is computing your integrals. 5.2, calculate for me a left sum and right sum with 4 rectangles.
We're starting from what?
4.2, the mean value theorem. So I'll put that 4.2 to 5.2. 4.2, 4.3, 4.4, 4.5, 4.6, 5.1, 5.2.
Okay.
Good? How many of you have a class right after this one on Monday?
Wait, what did you say?
On Monday, do you have a class right after this one?
I don't.
Because I can let you bleed over into the next class if you needed to take more time for your test. If you think you need more time, come a little bit early. Okay? Okay. But I'll put the review sheet on there as soon as I'm done with my next class, and then you guys get yourselves organized for your test.
Have a good afternoon.
Thank you.
Thank you.
Thank you.
Yeah, to be honest, I feel more fascinating. Yeah, I actually like this fundamental theory.
Because it has the word fun in it.
Are we gonna learn new stuff by the end?
Yes, that's what we do next. See, you already know how to do this, and you told me not to even put it on the test.
Studying.
There's no studying if you already know how to do it, duh.
Actually, I really know how to do it.
I hear a lot. No, here comes the boss. Time for me. Because in the next class.
I already told you, I know how to do it. But I found it for the writer.